I'm extremely honored to be included in this year's Chemical and Engineering News Talented 12, and have been enjoying the talk so far and look forward to hearing from the other honorees later today. That's the slide. Here we go. Okay. So I'd like to start my talk by first introducing my research background. I completed my undergraduate degree in chemical engineering from Washington University in St. Louis, and which is also where I'm from. And in my senior year, I had the opportunity to complete a senior thesis with the faculty advisor who would later become my PhD advisor, Dr. Jung. And during my PhD, I used surface chemistry techniques to examine interfacial reactions of nanomaterials in water and how nanomaterials could potentially be used to improve water treatment processes. And then after my PhD completed, I moved to California to work with Dr. Sedlak at UC Berkeley, investigating new materials for urban stormwater treatment, which I'll talk about later on in my talk today. And now I'm an assistant professor in the Department of Civil and Environmental Engineering at the University of Washington in Seattle. So I'd like to frame my talk by thinking about urban water sustainability. Traditionally, environmental engineers have viewed the urban water supply in a linear approach, where drinking water sources are used, treated, and then discharged. And this current paradigm is not sustainable for growing populations and urbanization. To protect this resource, a more sustainable approach would be to close this loop and recycle waste streams back to the consumer. And in order to do this, we would, of course, need to use a more advanced series of treatment processes. However, as you can imagine, there are some challenges to doing this, which is predominantly the presence of contaminants that persist even after this series of advanced treatment processes that will pose a threat to both human and environmental health. So my group, the Aquatic Innovations and Material Science Lab, is creating new technologies to address these problems in the urban water sector. My research bridges material science and surface chemistry with environmental engineering to investigate new ways to increase urban water supply sustainability. So I'd like to present two case studies during my talk today that shows how our group is working to address these problems. And the first focuses on stormwater management. So growing up in St. Louis and going to school in St. Louis, this was my experience with rain, is that we had too much of it. This is a picture of the St. Louis Arch and the Mississippi River nearby that's undergoing flooding due to excess rain. And then when I moved to California to conduct my postdoc research, I had another experience with rain in that there was too little of it. So when I was there in 2016, California had one of the worst drought years on record. And now that I live in Seattle, my dog Lucy and I are intimately familiar with rain. Okay, so again, let's think about this linear approach of how we even view stormwater, and that it's typically a nuisance, especially in urbanized areas with large impervious surface coverage. The excess runoff will lead to street flooding, and so typically what's done is we just convey the stormwater off the road and it's sent to discharging waters. Instead, better stormwater management approaches would be to create more centralized and decentralized low-impact systems, such as rain gardens, that can both convey stormwater off the road and promote local groundwater recharge, especially, again, in these highly dense urban populated areas. And alternative uses for urban stormwater could even be approaches like this, where we could locally harvest stormwater to use to irrigate our lawns and even to irrigate parks. And in cases of drought and extreme cases, we can use urban stormwater as a drinking water resource. But before we can realize these more sustainable approaches to urban stormwater management, we have to address the presence of contaminants in urban stormwater. So here are two examples of sources of contaminants that can exist in both urban and suburban conditions, and that's due to interactions with the stormwater with various surfaces as it travels throughout the streets and then eventually through storm drains down to receiving bodies of water. So let's, for example, take a look at a bioretention pond that's set in an urban area that's experiencing a storm event. You'll have an influx of contaminants into the bioretention pond that need to be treated. And you can take advantage of existing processes such as microbial degradation and filtration of large particles in stormwater, as well as some natural filtration processes of conventional media like sand and gravel. But my research group is looking at ways to implement engineered material and taking advantage of modifications of conventional media to help enhance stormwater contaminant in these bioretention ponds and in other grain stormwater infrastructure. So one example was the coffee biochar that was mentioned in the C&EN feature. And so ultimately what we're doing is thinking about the intended application of our materials and thinking about the way we want them to interact with the contaminants of interest. And so our group is essentially designing these materials and then synthesizing them in lab, applying the surface chemistry techniques that I employed during my PhD and postdoc studies, and then eventually applying them to treat water at the lab scale, and then eventually piloting these materials to treat real urban stormwater. The other case study I want to discuss is focused on presence of contaminants from wastewater discharge. And so one particular class of contaminants that we're interested in because they're so persistent are these per and polyfluoroalkyl substances, or PFAS. They're also dubbed the forever chemicals. These synthetic compounds were created for firefighting foams meant to extinguish liquid flames. So at training areas like the picture shown here, use of this foam would result in large groundwater contamination of compounds that have similar structures to the two compounds on this slide. And these compounds are also acutely toxic and can contribute to immunotoxicity, endocrine disruption, and potentially cancer. And unfortunately, it's not just this firefighting foam that these compounds exist in. They are so useful in many other applications, such as nonstick coating of pans and skillets, as well as water-resistant outerwear. And so they're starting to be used, or they have been used historically for many applications. And unfortunately, these compounds are so persistent that they are resistant to microbial degradation. They are resistant to natural degradation by UV light, and they are even resistant to degradation by traditional chemical disinfectants. And also, unfortunately for us, they're starting to pop up all over the country due to these widespread applications of these PFAS materials, and also at levels above the recommended EPA health advisory limit of 70 nanogram per liter. So the current treatment for PFAS removal is to use materials like granular activated carbon, as shown here. You might be familiar with this material as the active material in your Brita water filter for home purification systems. So there are a couple of disadvantages with using activated carbon to remove PFAS. Some of note are that this material is not selective for PFAS. So activated carbon is a widely available commercial adsorbent, and it's very effective at removing other co-contaminants as well. So typically in these systems where PFAS contamination exists, they're in very dilute concentrations. So you might have competition with other co-contaminants in the system. Also, activated carbon cannot be regenerated, and it can't be used to degrade PFAS. So my group is using a two-staged approach. We're first examining ways to selectively remove PFAS from water, and then using materials and, again, applying those surface chemistry techniques to investigate enhanced degradation of PFAS in water. So the first approach for selective PFAS removal is to use MIPS, or molecularly imprinted polymers. So during polymerization, you can include the compound of interest, which is then later extracted to create a polymer with an imprint specific to the target contaminant. So this results in a lock and key mechanism for highly selective contaminant removal. Another benefit to using this material is that you're able to regenerate the polymer for subsequent cycles of treatment. And after recovering PFAS from water, our group is exploring two methods for degradation. The first uses high energy sources to generate solvated electrons in solution. These strong reducing agents are able to effectively unzip the carbon fluoride backbone to generate fluoride in solution and degrade PFAS. So we're examining this approach to treat PFAS contaminated soil. And then the second approach that our group is using is exploiting these layered nanomaterials that have historically been used for energy storage applications, such as lithium-ion batteries, and using them as nanocatalysts in conjunction with a common chemical disinfectant to effectively degrade PFAS in solution. So what I've hoped to have shown here is both the challenges that exist with trying to increase urban water sustainability, but also the opportunities that our group are using to engineer novel urban water sustainability solutions. And again, we're doing that by thinking about ways to design new low-cost and sustainable materials, to implement them in many different ways to address issues at the urban water sector. And this primarily includes removal of these contaminants that persist even after full advanced treatment processes, but in the future, looking at ways to recover value-added products from waste streams, similar to Wendy's talk with the MOF material. And with that, I'd like to thank my amazing and diverse research group that made all of this work possible, and funding sources, as well as my mentors that helped me get to this point today. And with that, I'll be happy to take your questions. Thank you.
Thanks so much, Jessica. I was wondering, I know there are a lot of different types of MOFs. We have a MOF, or I'm sorry, not MOF, PFAS. There are a lot of different types of PFAS. We have a library at C&EN. Is this approach general for all of them, for removing them, or is it selective for certain ones?
Right, great question. So there's over 4,000, I think, different classifications of PFAS. And so it's a huge problem. And what we're currently investigating is which template compound works best to enhance selectivity of not just that template material, but general PFAS in solution as well. So that's something that we're playing around with in lab.
And someone asks, can you sort of reclaim and recycle the template to sort of avoid a PFAS release?
Yeah, so that's one of the benefits of using these MIP or molecularly imprinted polymer materials, is that they were first designed actually for drug sensing. So the idea of removing the template molecule during extraction and then reintroducing the polymer composite material that we're developing into solution that contain PFAS will result in this lock-and key mechanism, but then you can also use a simple kind of washing step to release or desorb the contaminant that's been attached to your MIP material, so that you essentially create a waste stream that's concentrated, we hope, in just PFAS and not other co-contaminants that are going to be present in these systems. And so once we generate a waste stream that is concentrated with these PFAS, then we can do the next step, which is the degradation techniques, more effectively. Because one of the issues with the current experimental technologies to degrade PFAS in solution is that you need really clean systems to do this in. So ideally, you just need water and PFAS and whatever reactive materials you're using to degrade these compounds. So by doing this selective adsorption, desorption step prior to degradation, we're creating essentially a holistic approach to PFAS treatment.
All right. Someone else asks a follow-up, and you may have just answered this. Is there a preference between acids and sulfonates in PFAS? I guess most destruction techniques currently favor carboxylic acid degradation.
Right, great question. So there are differences in reactivity between the carboxylated PFAS and the sulfonate PFAS. Our MIP material, we're developing currently PFAS that are using, or the mixed materials that are using the carboxylate and the sulfonate as a template materials to help capture the two kind of main sources of the perfluoroalkyl acids. Our degradation approaches, however, do work for both the sulfonate and the carboxylate groups. So that's been really promising.
All right. Well, thank you very much, Jessica. I really enjoyed your talk.